So in the last class, we have completed Thevenin's theorem. Before that, you have studied superposition theorem. So till now we have completed two theorems. Is there any doubt in these two theorems? If there is no any doubt, then I will go through the third theorem, that is this Norton theorem.
Sir?
Hmm.
Sir, can you please explain Thevenin's theorem again?
Okay. Briefly, I will explain the Thevenin's theorem, how we can apply. Okay. So as per the statement of Thevenin's theorem, if there is a network, that is network should be linear active network, RLC network. So if there is a network and across any two terminal of network, if we have to apply Thevenin's theorem, so firstly we have to remove the elements connected in between two terminals. Okay. So it means as per the statement of the Thevenin's theorem, across any two terminal of linear active network, the network can be replaced by a single voltage source and in series with the equivalent impedance. That voltage source will be VTH, that is Thevenin voltage, and equivalent impedance will be Thevenin impedance. Okay. In place of impedance, we can call as a equivalent resistance also if there is a resistive network. So how we can calculate VTH or Thevenin voltage? Thevenin voltage is the voltage which we will evaluate by removing the element connected between the two terminals. Okay, that is, so it is shown here, terminal A and B. So firstly, we will remove the elements connected in between these two terminals, and there is open circuit created. And we will evaluate the Thevenin voltage across these open circuit terminals. And that's why this voltage is also called as open circuit voltage, VOC. Okay. So we can calculate this value by solving this remaining network by using any method. Okay. That we have studied earlier. So we can use Kirchhoff's law, we can use node method, we can use mesh method, you can use superposition theorem. So whatever the circuit solving techniques you can apply anyone. Okay, as per the simplicity and as per the complexity of the network. And there is a procedure to evaluate this Thevenin impedance. To evaluate Thevenin impedance, firstly, we will evaluate across these two terminals only. So what we will do, we will eliminate all independent sources. Okay. It means the independent sources, voltage sources and current sources are there. You know that independent sources will be replaced by their internal resistance, and for voltage source internal resistance is 0. For current source internal resistance is infinite. So that's why voltage source will be short circuited as resistance is 0. Resistance 0 means voltage is equal to 0. It means it will be short circuited. Resistance infinite, it means current 0. So it will be open circuited. Okay. So current source will be open circuited, voltage source will be short circuited. So first procedure is to remove the load resistor. Okay, in between connected in between the two terminals of any network, and then open circuit is created, and we will evaluate the open circuit voltage, that is called as a Thevenin voltage. Then to evaluate ZTH, we will evaluate across these terminals only, and we will eliminate all independent sources by their internal resistance, and we will not touch dependent sources. That's it. Okay. After evaluating VTH and RTH or ZTH, we will make Thevenin equivalent circuit, and that will be the series combination of VTH and ZTH. Clear? And to evaluate the current flowing through the element, that initially we have to calculate. For that, we will again connect the removed element. Okay, the load resistor we have removed, So we will again connect in between these two terminals. And this is a simple circuit. You can see that it is a simple single loop is there. So we can easily calculate the current flowing through this branch, and that will be IL is equal to VTH upon RTH plus RL. Okay, RTH plus RL both are in series. So I think now it is clear to all of you. Okay.
Yes, sir.
Have you tried to solve these examples, example 2 and 3? I was also given for superposition theorem. To apply superposition theorem, I was also given the previous example that we have taken for the analysis of, this one, example 3, we have taken for the analysis of node method and mesh method. So if you will apply the superposition theorem, so you can see that there are two sources here. Each source at a time you have to consider, and you have to eliminate other sources, okay, in the circuit. And then you have to calculate the current flowing through the branches by considering a single source, okay, at a time. Then next time you have to take each sources at a time. So based on the number of sources available in the circuit, and we will take only independent sources, okay. So based on the number of independent sources in the circuit, we have to solve the circuit in superposition theorem accordingly, okay. Suppose there are three sources in the circuit, so we have to solve three different circuits by taking individual sources at a time, okay. And then we have to take the responses by considering each source at a time. And in the final stage, to find out the resultant current, we had to take the algebraic sum of all currents evaluated by considering each sources. So that is the summary of superposition theorem. And how many of you have tried this one? Have you tried example number 3 that we have taken for nodal and mesh analysis? If you have not tried yet, try it and match your answer, whatever we have received, the values of I1, I2, I3 by applying nodal method and mesh method, okay. Now I will start the next theorem, that is Norton's theorem. And Norton's theorem is nothing but it is a dual of Thevenin's theorem. Dual of Thevenin's theorem means in Thevenin's theorem you can see that the in between any two terminal of a network, we can replace the whole network by a single voltage source in series with the impedance, okay. If you apply the source conversion principle here, you can see, you know that the voltage source can be converted into current source, and the condition is that together with the voltage source there must be a series resistance, and that you are achieving in this Thevenin's theorem. In Thevenin's theorem, VTH and RTH both are in series, so this can be converted into current source, and the current source value will be VTH divided by RTH, and across that current source you have to apply same resistor here, okay. So Norton's theorem is nothing but source conversion, okay, means voltage source to current source conversion. So that's why it is called as it is a dual of Thevenin's theorem, okay. So it means, like Thevenin's theorem, firstly we have to eliminate that element connected in between these two terminals, okay. That the same procedure will be there just like Thevenin's theorem, but we were creating open circuit and we was calculating the open circuit voltage across these two terminals AB. Now we will do what we will do. We will short circuit terminals A and B, means we will connect a simple wire with very low resistance in between terminals A and B, and we will calculate the current flowing through this terminal A and B. Okay, means the short circuit current. If you do short circuit in between these two terminal, you have to calculate short circuit current, and that will be your ISC, short circuit current. Okay, and it is nothing but Norton current. It is also called as a Norton current, IN. And Z equivalent is nothing but, it will be same, the procedure is same, just we have used in the case of Thevenin's theorem, the same procedure will be there to evaluate the equivalent impedance. Okay, so Z equivalent is nothing but ZTH, that is Thevenin's theorem and Thevenin impedance, and it is in Norton's theorem it is called as Zn. Okay, Norton impedance. So Norton equivalent circuit is nothing but a current source in parallel with impedance So this is Zn, this is In. In is called as ISC, short circuit current, because in this method you will create short circuit in between these two terminals. Means you will connect simple wire in between these two terminals and you have to calculate this short circuit current, ISC. This is the simple procedure. Okay, just only the change is, in place of VTH, we have to evaluate short circuit current. The procedure of evaluating Z equivalent or ZTH or Zn is same, means all are equal. Clear? Is it clear to all of you? So Norton's theorem is the dual of Thevenin's theorem. Is there any doubt?
डिपेंडेंट सोर्सेस को भी इसमें सेम थेवेनिन जैसा ही करना है क्या?
बिल्कुल, डिपेंडेंट सोर्सेज वाले जब करेंगे तब बताएंगे। डिपेंडेंट सोर्स को भी थेवेनिन्स की तरह ही करना है। नॉर्टन्स थ्योरम में भी हम डिपेंडेंट सोर्सेज को लेके हम कर सकते हैं। ओके, अभी ये प्रोसीजर समझ में आया?
हाँ, आ गया।
थेवेनिन्स थ्योरम में हम एलिमेंट को हटाने के बाद ओपन सर्किट करते थे, ओपन सर्किट हो गया तो वहां पे ओपन सर्किट वोल्टेज कैलकुलेट करते थे, वही हमारा VTH थेवेनिन वोल्टेज होता था। यहाँ पे ओपन सर्किट ना करके एक सिंपल वायर कनेक्ट कर देंगे दोनों के बीच में और शॉर्ट सर्किट क्रिएट कर देंगे, और उस शॉर्ट सर्किटेड टर्मिनल के क्रॉस हम थ्रू हमें करंट कैलकुलेट करना है जो कि ISC होगा, शॉर्ट सर्किट करंट। ओके, और यही शॉर्ट सर्किट करंट हमारा होता है नॉर्टन करंट। सो ISC इज नथिंग बट नॉर्टन करंट। ओके, and the procedure of calculating Z equivalent is same, just like we have seen in the case of Thevenin's theorem. So according to the Norton's theorem, it states that any two output terminals AB of a linear active RLC network containing one or more independent or dependent voltage or current sources can be replaced by an equivalent current source, that is Norton current, and a parallel impedance Zn. Okay, so this is the Norton equivalent circuit, this one, where a short circuit current is kept in parallel with Zn. Okay, and this is the equivalent circuit of Norton theorem. And the procedure is same to evaluate Zn. Zn is the equivalent impedance looking into the terminal pair AB with all independent sources has been replaced by their internal resistances. So you know the procedure that for ideal sources, ideal independent sources, current source will be open circuited, voltage source will be short circuited. So procedure is same here. In figure 4a, you can see that previously this element was connected in between terminal A and B. So first procedure is to remove this element and make short circuit in between these two terminals A, B. So in the first step, short circuit is created and the current direction IN is denoted here. That is Norton current or short circuit current you can denote. Then in the second stage, we have to calculate the Thevenin equivalent, Norton equivalent impedance, that is Zn, and Zn is equal to Z equivalent, and that will be equal to ZTH. Okay, so same procedure will be there. Means across these two terminals only, we have to calculate the equivalent impedance. So what we will do, we will eliminate all independent sources. So all independent sources will be eliminated, means voltage sources will be short circuited and current sources will be open circuited. If there are any dependent sources, we will remain as it is. Okay, they will remain as it is. So in step 4, Norton equivalent circuit, for Norton equivalent circuit, after calculating Zn and In, we have to place in parallel, and that will create Norton equivalent circuit. So this is Zn, this is In. So this is nothing but Norton's equivalent circuit. Okay, this is called as a Norton equivalent circuit. Just like in Thevenin's theorem, we have placed Thevenin voltage and Thevenin impedance in series, and that was called as Thevenin equivalent circuit. Okay, similar to that, it will be Norton equivalent circuit. Now what we will do, again, just like previous theorem, we will again connect our element we were disconnected from the terminal A and B. So we will connect the same element and we will calculate current flowing through this element. Okay, so in this case we have considered as a load resistor RL. Current flowing through this is IL. So what will be the value of IL? IL can be calculated simply by using current division rule. So as per the current division rule, you know that if we want to calculate the current here, and in these two parallel branches, you can see that the main current is flowing here, IN, and at this terminal, both are splitting. Okay, there are if this is I1 and this is IL, so you can see that at this terminal, if you will apply KCL, so both are splitting from here. So IN will be divided in two parts, I1 and IL. So what will be the value of IL? IL is nothing but the supply current IN multiplied by, in the numerator, you have to take this opposite resistor or opposite element value, that is Rn divided by sum of these two, Rn plus Rl, and that is, you can see here, IL is nothing but Rn upon Rn plus RL into In. Okay, according to the current division rule, we can easily calculate the value of current flowing through the load. Is it clear to all of you?
Yes, sir.
Similarly, the voltage across load we can calculate. That will be the voltage drop in between across this load resistor RL, and that will be VL is equal to IL into RL, and power absorbed by the load, that is PL is equal to IL square into RL, IL square into RL. Okay, because you know that in resistor power dissipation can be calculated by power is equal to I square R. So here IL is the current, so IL square into RL, that will be power absorbed by the load. So it means from here, if you compare the Thevenin's and Norton's theorem, IN is nothing but VTH upon RTH, means Norton current or short circuit current is nothing but VTH upon RTH, and RTH is equal to RN, means the Thevenin resistance is equal to Norton resistance. Okay, so by comparing these two theorems, Thevenin's and Norton's, you can write the resultant expression, and in this way we can call it as a Thevenin's theorem and Norton's theorem, both are dual to each other. Okay, so in this same example, we will take that we have taken in the Thevenin's theorem, okay, and superposition theorem also. Means we have to calculate the current flowing through the branch connected in between terminal A and B, that is, this is IAB, and the voltage across VCG, this C and G nodes. Okay, voltage in between C and G, VCG, means the voltage across this current source. So the same element we have, same network we have considered. So first procedure is to eliminate or to remove the element connected in between these two terminals A and B. So first we will remove this element, that is 1 ohm resistor from here, and then we will make a short circuit between these two terminals A and B by connecting a simple wire, and we will calculate the current flowing through this branch. So IN is denoted here, that is current flowing through this branch, IN. So you can see that now you can look that there are three loops, individual loops in this circuit. So if you use the mesh method, so it will be easy to solve the circuit, and to apply mesh method, you know that firstly we have to denote, you have to identify the number of meshes. So here are 3 meshes, and we have to denote the current flowing through the meshes in clockwise only for simplicity. So I1, I2 and I3, we have denoted the mesh currents in loop 1, loop 2 and loop 3. Okay, so KVL in loop 1, by applying KVL in loop 1, 3 minus R4 into I1 minus I2, 3 minus R4 into I1 minus I2 is equal to 0. How you can directly write? for this you have to assume that I1 is, if I1 is dominating, so in this branch R4, the current flowing will be I1 minus I2, and the overall direction will be downward, I1 minus I2. Okay, if the current direction is downward, the current, you know that the current will flow in element from higher potential to lower potential. So that's why plus will be here, minus will be here. So if you will apply KVL in loop 1, you can start at this point. So minus plus is plus 3, then plus minus is minus, minus R4 is 2 into I1 minus I2, and that is 0. Okay, so that what it is written here. And you know that I2 is nothing but minus 2 ampere, because I2, the direction of I2 is this way, and the direction of current source is 2 ampere. So you know that the same current will flow in this branch, and that is equal to I2. So that's why, as per our assumption, we have taken the clockwise direction of current here. So I2 will be minus 2 ampere. Okay, because the actual current source direction is upward here, and we have taken downward direction. We have assumed downward direction. So that's why I2 will be minus 2 ampere. So by putting the value of I2 minus 2 ampere, we can solve further that 3 minus 2 I1 plus 2 into I2. I2 is equal to minus 2 is equal to 0. So 2 I1 is equal to, this is minus 4 plus 3, that is minus 1. So I1 is equal to minus 1 by 2. Minus 1 by 2 means minus 0.5 ampere. That is I1. Okay, so we have evaluated I1 and I2 values. Now by using a simple another equation, we can easily calculate the value of I3. Okay, so if we apply KVL in loop 3, so we can calculate the value of I3. The current flowing I3 we have assumed here, so it means plus minus. Okay, in this branch there are two currents. One is I2 flowing in this way, I3 flowing in this way. So we can assume any one dominating. So if we are assuming that I3 is dominating, so polarity will be plus minus here, and the current flowing through this branch will be I3 minus I2. Okay, so applying KVL in loop 3, by applying KVL in loop 3, if we can start at this point and we will reach again at this point, we have two elements to cover. Okay, so firstly plus will come, so plus minus is minus 3 into I3. Okay, now in this branch 4 ohm resistor is there, plus minus, it will be minus 4 into I3 minus I2 is equal to 0. So it means 3I3 plus 4I3 minus 4I2 is equal to 0. 7I3 is equal to 4I2. So it means I3 will be equal to 4 by 7 I2. So it means I2 we have to put minus 2. So minus 8 by 7 ampere. That will be I3. I3 will be minus 8 by 7. Yeah, this is written here, minus 8 by 7. So what will be the Norton resistance? The value of Norton current, IN. IN is the current I1 is flowing in this way, current I3 is flowing in this way. This is I3, this is I1. So IN is nothing but the direction is in this from A to B. So that's why you can see here I1 should be dominating. So IN will be equal to I1 minus I3. IN will be equal to I1 minus I3. We have evaluated the values of I1 and I3. So if we will put, we can easily calculate the Norton current value. And the current will flow, if we are getting here the positive value of IN, so the current will flow, current is flowing from A to B. Clear? So we have calculated the value of IN, and Rn, that will be same as RTH. So RTH we have evaluated in the previous, that in Thevenin's theorem, RTH is equal to 1.555 ohm. That will be your Rn, same. So we will make Norton equivalent circuit, and then we will connect again the removed element in parallel, and we will calculate the value of IL, that will be equal to Rn divided by Rn plus Rn into IN. So 1.555 divided by 1.555 plus 1, because RL is equal to 1 ohm, multiplied by IN. IN is, just we have evaluated, IN is 9 by 14 ampere. So 9 by 14 is 0.643. So by putting the value of this, we are getting 0.39 ampere and current flowing from A to B. So we have got the same value of IL that we have obtained in the case of Thevenin's theorem. So it means it is verified by using this Norton's theorem also, that the same current we are getting that we have obtained by using Thevenin's theorem. Okay, and the procedure of evaluating the VCG is same, just we have seen in the case of Thevenin's theorem. So is there any doubt in this theorem, Norton's theorem? The only thing is that you have to practice by your own. If you are not practicing, you will be confused. Okay, every time when there will be new problem, you will be facing some difficulty while solving the problem. So that's why you have to practice a lot. You have to take 1-2 examples of good examples of circuit, and you have to apply all theorems one by one, and you have to verify your answer whether you are getting correct or not. It will give you confidence. Okay, if you will try by your own, by taking separate examples, by taking good examples, so and you'll if you'll apply all theorems, that will boost your confidence, okay, in solving questions. Hello. Yeah, hello. Sorry, I got a call. Okay. So I think the procedure of applying Norton's theorem that uh, you have got, and you have understood the procedure how we can apply Norton's theorem and why it is dual to the Thevenin's theorem. Okay. So there are some examples, example number 2 and 3, that you have to use. Example number 2 and 3, you have to solve these examples and you have to verify your answer that is given here, that IL is equal to 2.625 ampere, means current flowing. Where is IL? Find IL through 6 ohm resistor. Okay. This is RL. So you have to assume current IL here and you have to calculate the value of IL. So how we can how we can apply the Norton's theorem to calculate the value of IL? How we can start? Can anyone tell how you can start? You have to assume two terminals, two nodes. You have to assume two nodes. This node 1 means, suppose this is A, this is B. Okay, because this load resistor is connected. Load resistor means you have to calculate the current through 6 ohm resistor. That will be your load resistor RL. Okay, so load resistor 6 ohm we have assumed. So what will be the first procedure to apply Norton's theorem? Can anyone tell?
शॉर्ट सर्किट दबाए
First procedure is to remove that element connected in between these two terminals. So firstly we will remove this element, right? 6 ohm. And we will make short circuit in between these two terminals. And we will calculate, means first we will remove the element connected in between the terminal AB, and then we will make short circuit by simply connecting a wire in between these two terminals. And we will calculate Norton current in flowing through this wire. Okay. And the current direction, we have assumed that the current is flowing from A to B. Clear? So we have to solve the circuit and we have to calculate the value of IN. Right? So first procedure is to calculate the value of IN by creating short circuit in between these two terminals AB. What is the next procedure? What is the next procedure?
We will
शॉर्ट
apply
सर्किटिंग वोल्टेज
KVL.
सोर्स
No, next procedure means first,
short circuiting voltage sources and open circuiting current sources.
suppose we have calculated the value of IN, okay, by solving this network. What is the next procedure? What we have to evaluate next? We have to evaluate, because it is a resistive circuit, so we have to evaluate RN, that is Norton equivalent resistance, Norton resistance, equivalent resistance or Norton resistance. So how we can calculate Norton resistance? How we can calculate Norton resistance?
removing all the independent source,
Hmm.
and then we can connect.
What we will first remove this element. Okay, ये एलिमेंट तो हमने रिमूव किया ही है. यहाँ पे ये ओपन सर्किट हो गया है ए और बी. In between A, B, we have to calculate equivalent resistance, means RAB, R equivalent, by eliminating all independent sources. You know that independent sources, voltage sources and current sources are there, and voltage sources will be short circuited, current sources will be open circuited. So when we will do short circuit of this voltage source, it will be short circuited. It will also be short circuited because it is an independent source, by assuming ideal sources, because there are no the internal resistance given for these sources, and this current source will be open circuited. Okay, this current source will be open circuited. So we have to calculate RAB, that will be your R equivalent, and that will be Norton resistance, RN. So which resistances will be in series, which will be in parallel? When these two are short circuited, which two resistances will be in parallel?
Sir, 4 ohm and 8 ohm resistance.
These two, है ना? This 4 ohm and 8 ohm, both are in parallel, because you can see that if it is a short circuited, this is also short circuited. So they are connected with a common terminal, okay, here. So this 8 ohm and 4 ohm both are in parallel. So parallel combination will be 4 into 8 divided by 4 plus 8, 32 divided by 12. Okay. And what next? Then we have this type of circuit. Where this is 2 ohm. This is 32 by 12. 32 by 12 means 8 by 3. 8 by 3 ohm. This is A, this is B. We have to calculate RAB. So what will be the value of RAB?
Series
14 by 3.
combination.
Series combination, that is 8 by 3 plus 2. So it will be 14 by 3 ohm. Okay. So if you have calculated IN, so simply you have to make Norton equivalent circuit. This will be your IN. This will be your resistor. And in between these two terminals AB, you have to connect the resistor that you have previously removed to apply Norton's theorem. IN, this is RN, this is RL. RN is equal to 14 by 3. RL is equal to 6 ohm. And you have to calculate the current flowing through this branch. That will be IL. Clear? Okay. Okay, so last network theorem is left, that is maximum power transfer theorem, and it is also the application, it is an application of Thevenin's theorem only. Okay, and by this theorem we will identify how much power will be transferred, means how much maximum power can be transferred from source side to load side. Okay, and we will generate the relationship for that, and what will be the condition to transfer power from source side to load side. and how much maximum power can be transferred. That we will see in the next class. Now I will take your attendance. Please. Okay. Ashish Chandra,
Present, sir.
Avya,
Present, sir.
Aditya,
Present, sir.
Akash, Akhilesh, Akshit,
Present, sir.
Anand,
Present, sir.
Ankit,
Present, sir.
Apurva,
Present, sir.
Arnav,
Present, sir.
Avinash,
Present, sir.
Ayush,
Present, sir.
Avinash. Oh, sorry. Avinash. Gaurav,
Present, sir.
Nishant,
Yes, sir.
Krishna,
Yes, sir.
Maitri,
Present, sir.
Mudra, Paranjay,
Present, sir.
Prachi,
Present, sir.
Prajwal,
Present, sir.
Priyansh,
Yes.
Priyanshu,
Present, sir.
Pulakit,
Present, sir.
Rahul, Rajiv, Rishabh, Rohan, S. Ritik Sai,
Present, sir.
Saket, Samyak, Sangram,
Present, sir.
Sasank,
Present, sir.
Subham,
Present, sir.
both Subham are there. Okay.
Present, sir.
Srajan,
Present, sir.
Sudhanshu,
Present, sir.
Sujit,
Sir,
Sujit, Sumit, Sikarwar, Supriya,
Present, sir.
Suryans, Saket, Suman. Saket, Suman present?
Yes, sir.
Okay. Supriya,
Present, sir.
yeah, completed Supriya. Suryans, Ujjwal,
Present, sir.
Utkarsh,
Present, sir.
Vaishnavi, Vedanshi,
Present, sir.
Vishal,
Present, sir.
Yash,
Present, sir.
Vinita Bharti,
Present, sir.
Shambhavi. Okay.
Present, sir.
Okay.
Sir, sir, I wanted to ask one thing. Sir, हमारे टाइम टेबल पे लिखा है कि there is a computer programming subject as well, which holds 312 credit points. So, sir, वो क्लास अभी होती नहीं है हमारी, तो वो ऑफलाइन शुरू होगी?
कंप्यूटर प्रोग्रामिंग अभी नहीं स्टार्ट हुआ है.
No, sir.
Okay. So in offline mode, I think there are more hours will be for lab. Okay, computer lab. So that's why I think they have not started yet. So in offline, definitely it will start, and You will have computer programming course and lab as well, both.
Okay, sir.
Okay, then you can join your next class.
Sir, Sumit Sikarwar present.
Sumit Sikarwa. I think computer programming is in your second semester, not first semester. Okay. If it is there in your timetable, if is there in your
So timetable, sir, it is not there in timetable, but it is there in the syllabus. It is of, I guess,
No.
13.
I think if it is there in timetable, then it is okay. But if there is, if it is not in your timetable, so it will be in second semester, I think. Okay, no issues.
Okay.
Okay, thank you. Thank you.